In the previous video, we introduced the multilinear regression model and the matrix notation for representing this model. In this video, we'll define the least squares regression loss function and use geometry to optimize the loss. So we begin by defining the loss. In this lecture, we'll consider least squares regression because it's easy to optimize and widely used. Least squares regression implies the least squares loss, which is just a squared loss we've seen before. Particularly, we'll take the average squared loss over our data, which looks like this. You'll notice a small change in notation from what we've used in the past. In particular, we've adopted the matrix notation from the previous video. When we look at the subscript I, here we're referring to the ith row of the y, the response variable y, and the ith row of the matrix x, which means that x sub I is actually a row vector, the ith row vector, with the 1 added at the beginning. So that's the standard average squared loss. We can rewrite the squared loss in matrix notation. So here we've written the loss in terms of the column matrix y and the data matrix, or the covariate matrix, x times theta. We can further simplify this summation into a product of two vectors, in fact, a dot product of the residual vectors. So here, again, the x theta is simply our y hat, our predictor, our estimate, and y is the observed value, and so this is just the residual, as shown here. All right, so now we've defined the loss. We would need to minimize the loss. How should we minimize this loss? Well, we've already looked at calculus-based techniques. And in fact, you can use calculus-based techniques to minimize this loss. And in previous versions of this class, we've actually used that. But it can get a little bit complicated because we end up needing to use matrix calculus. You could apply gradient descent. And that's actually a pretty widely used technique when these models get really large. But in this lecture, we're going to actually look at geometric reasoning. And so we'll use geometric reasoning to come up with an analytic solution to the loss minimizing theta for this problem. So the way to approach this is to first realize that y hat, our prediction, is actually just a linear combination of the columns in x. To see that, consider y hat. So y hat is going to be a vector with n rows in one column. This is the predicted value for every row in our table. Our covariate matrix x has two columns. X colon 1 refers to the first column of x, and x colon 2 refers to the second column of x. So this is going to be an n by d plus 1 matrix in general. Remember, the plus 1 is because we've added an additional ones column. But here we're just going to look at a two-column x covariate matrix. And as before, our parameter vector is going to be in d plus 1 dimensions, but in this particular example, it'll just be a two-dimensional vector, or two rows and one column. Taking this product then becomes the linear combination of the first column vector and the second column vector, so theta 1 times the first column plus theta 2 times the second column. This linear combination lives in a two-dimensional subspace of an n-dimensional vector space. So here we can try to visualize this n-dimensional vector space. Now granted, I only have 3 dimensions drawn here and really only 2 dimensions that you can see on your screen. But bear with me. These two column vectors live in this n-dimensional space, but they actually form a two-dimensional subspace in this n-dimensional space. And in fact, any point in this two-dimensional subspace is simply a linear combination of these two column vectors. And so the y hat that we can predict, x times theta, must live in this two-dimensional subspace. Now, our response variable, y, that we observe, is not constrained to live in this two-dimensional subspace and can live anywhere in this n-dimensional vector space. The residual is the vector between the subspace spanned by our two column vectors and the observed y that lives in our n-dimensional vector space. So we'd like to minimize this squared residual, or this squared distance. How can we do that? So one way to do that would be to make sure that this residual vector is perpendicular to this vector space. So we want to make sure that the distance of this vector is short as possible. So we want this point in this two-dimensional vector space, so this point right here, really determined by x times theta, to be as close as possible to this y while staying inside of this plane. And we can do that when this line here is perpendicular to this plane. So we want to make the residual perpendicular to this two-dimensional subspace. Another way to say this is we want the residual vector to be orthogonal to the subspace spanned by the column vectors of x. By the definition of orthogonality, we want this residual vector y minus x times theta hat. Here, theta hat is going to correspond to our optimal choice of theta. We want this residual vector to have no component in the subspace spanned by x, which means that the dot product of the residual vector with this subspace should be 0. So this definition of orthogonality means that there's no component of this orange vector that lives inside of this space. So using simple linear algebra, we can multiply the x transpose through the parentheses. Further rearranging terms, we get x transpose x times theta hat equals x transpose y. And this is the famous normal equation. Here, x transpose x is going to be a d plus 1 by d plus 1 dimensional matrix. Theta, again, is a d plus 1 dimensional vector. And x transpose y is also going to be a d plus 1 dimensional matrix. Now, if we assume x transpose x is a full rank matrix, then we can invert x transpose x and solve for the optimal theta hat that minimizes this loss. And so this gives us theta hat equals x transpose x inverted times x transpose y. And so this is the solution to the normal equations. So to recap, we defined a multilinear regression model. Y hat, our prediction, is equal to a linear combination of the columns of x. We use the average squared loss, or we define the average squared loss as the inner product of the two residuals, or the sum of the square of the residuals. And then we use geometry to minimize this loss. So the solution, theta hat, which is our best estimate for the value of theta in this model here, is simply x transpose x inverse times x transpose y. And this is the solution to the normal equation. And again, we derive this just by using the geometry of the space. So that concludes this part of the video lecture. In the notebook below, we'll actually work through solving this linear system.